everyone, welcome back to our course Manufacturing Processes. Today we are going to discuss about week 2 materials in manufacturing. Basically today we are going to discuss about fundamentals of metal casting process. So overview of metal casting technology, heating and pouring, solidification and cooling. These are the topics we are going to discuss. Solidification process, as you know, liquid in a highly plastic condition. So metal is melted, metal will get converted to liquid or in a highly plastic condition. This molten metal is poured into a cavity, and after solidification we produce a part or a product. This process is called a casting process. We already have studied it in week 1 material, how a casting process is performed. So a metal, after heating, it gets converted to a molten metal. Molten metal is poured into a mold of desired shape. So after solidification, liquid metal get converted into a solid desired shape or part. That part is the final finished part in a casting process. So what are the materials that can be casted? The materials that can be casted are metals, ceramics and polymers. Now solidification process can be divided as casting of metals, glass working, processing of polymers. So today we are going to discuss about casting of metals. There are two types of casting. Expendable casting means sand casting. We are using the mold only for one time, and after the casting process we break the mold and take out the product. So only one time we can use the mold. But in permanent mold casting, a metal mold is used. We can repeat the process. That means many products can be produced using the same mold. So permanent mold casting are economical whenever it is used for a mass production, and sand casting is basically job order work. Now casting process involves three stages. First stage, we have to melt the metal. Metal, when it gets heated, it reaches its melting point. After absorbing latent heat of fusion, it gets converted into liquid metal, and then this liquid metal is poured into a mold. But after reaching the liquid metal, you have to increase the temperature again to pouring temperature around 100 degrees Celsius above melting point. You have to heat before pouring. So at that temperature, the molten metal is poured into a mold or a cavity, and after freezing, after solidification, we produce a product. This is the casting process. Now, what are the advantages of casting? As I explained before, the advantages are very complicated and intricate shapes can be produced. Both external and internal shapes can be produced. We can reach a net or near net shape products, and we can even cast very large parts. What are the disadvantages of casting? The disadvantages of casting includes some of the limitations on mechanical properties. We cannot increase or improve certain mechanical properties, and one of the main disadvantage is its accuracy. So because of shrinkage, we cannot maintain the exact size of the product. Hence, accuracy is slightly less in comparison with other manufacturing process. Surface finishing also another concern in sand casting process, because the finishing will not be there. The surface will be rough, and we may have to do machining before it reaches the customer. Then safety hazards, we are dealing with molten metal at very high temperature. We can say very high temperature, and this molten metal definitely is dangerous to the workers. So safety hazards to workers due to hot molten metals. Environmental problems due to fumes and other oxides, etc., may produce environmental problems. So which parts can be produced using casting? Casting can be produced using big parts like engine blocks, engine cylinders, heads for automobile vehicles, machine frames, railway wheels, pipes, big statues, pump housings. These are some of the parts which can be produced by casting. Then small parts, if you see dental crowns, jewelries, small statues, frying pans, these are made by casting. So in day-to-day life, many of the products you come across are made by casting process, and the place where we do casting, that place is called a foundry shop. The factory equipped for making mold is called a foundry shop. Now we have seen sand casting. What are the parts of a sand casting? The parts of a sand casting consists of a flask. This flask consists of drag and cope. Lower part is called drag and upper part is called cope. Sorry, there is a pouring cup to reduce the splash and turbulence. When molten metal is poured into the pouring cup, that turbulence will get reduced, and in the downsprew, the molten metal moves through the downsprew. It enters the bottom side, and then it enters the riser where metal is stored, and then this metal flows to the cavity or the mold where we need a desired shape. So molten metal continuously flows from the riser to the cavity, and it acts like a reservoir. So these are the different parts of a mold, a sand casting mold, and core is a solid part which is inserted in the mold to produce hollow or hollow portions, or to produce a hole. We are using core inside the cavity. There are two types of casting processes: expandable mold processes and permanent mold processes. Expandable mold process means we need to break or destroy the mold and then take out the casting. Only once we can use the mold. Permanent mold means it can be used again and again, usually made up of a metal. This is mainly used in mass production. So advantages of casting already discussed: intricate geometries, very complicated geometries can be produced. Permanent processes are economic whenever we go for mass production. So riser, as I already explained, riser is a reservoir to store molten metal and then allow the molten metal to easily flow into the cavity. Uh, so the flow will be smooth because of the riser. The riser must be designed to freeze after the main casting in order to satisfy its function. So casting will be solidified first, and then the riser will get solidified. This need to be designed. The shape of the riser need to be designed according to the casting. So heating the metal. So what are the stages of heating? First step, we need to heat it to raise the temperature to the melting point. Then supply heat to convert solid to liquid. Then supply heat to change or to increase the molten metal temperature to the pouring temperature. So three stages of heating takes place in casting. Pouring the molten metal, pouring temperature, pouring rate, turbulence, these are all factors which affect the efficiency of the process. So pouring temperature minimum, it like around 100 degrees Celsius more than the melting. Pouring rate and turbulence of the molten metal, these are very important in the case of a casting process. One thing we need to make sure that metal must flow into all regions of the mold most importantly to the main cavity before it gets solidified. Solidification of metal, it takes place in two categories, a pure element or an alloy. So if it is a pure element, solidification process is different, and if it is an alloy, it is different. So transformation of molten metal or cooling of molten metal back to solid state is called solidification. This is a very important process in casting, because after pouring, the molten metal reaches the mold and then it gets solidified or it gets cooled. It releases heat and then it becomes solid. So this process is different if it is a pure element, like if it is aluminium, or like it is copper, or if it is a steel, it will, if it is steel like an alloy, it will be totally different. Now, cooling curve for a pure metal, if you look at it after pouring, what happens? This is the cooling curve for a pure metal. It is not an alloy. That means it has only one element. It's a pure metal. Now, pouring temperature. So this is temperature versus time. The graph is in y-axis is temperature and x-axis is time. After pouring, what happened? The temperature of molten metal reduces consistently. It reduces, cooling takes place, and at a particular point called melting point, what happens? Freezing starts. So the metal will start converting to solid. So from pouring point, when you pour the molten metal, it reaches the cavity. After reaches the cavity, what happens? Cooling takes place constantly, and then at melting point, freezing starts. Then solid amount of solid increases by time. As the time increases, at the same temperature, look at that, at the same melting temperature, it releases latent heat, and then liquid metal slowly get converted into solid. At this point, it will be 100% solid. So it takes some time for converting liquid molten metal to solid molten metal, solid metal, and this time is called local solidification time. So what happens in here? When we pour molten metal, constantly liquid cools, and at a point freezing starts, and then freezing continues at the same temperature, and then at a point the liquid, it gets completely converted into solid. Then again the solid after has to be cooled. It cools, and then after some time it reaches the ambient temperature. So the total solidification time means time at which liquid metal is poured, and then time at which solid it becomes 100% solid. That is called total solidification time. Remember one thing, in a pure metal like aluminium or whatever it is, if it's a pure metal, the freezing or solidification, liquid to solid transformation takes place at the same temperature. If it is an alloy, what happens? If it is an alloy, from pouring temperature, freezing, from pouring temperature, as it the temperature decreases consistently, and at a particular temperature, what happens? Freezing begins, and then freezing continues, and the temperature also get reduced. This is the difference between alloy and a pure metal. In pure metal, as the freezing starts and freezing ends at the same temperature in the case of a pure metal. But if it is an alloy like steel, freezing start at a point, and then the temperature also decreases with time, and at a particular temperature, the complete amount of liquid will get converted to solid. So this freezing takes place over a temperature range rather than a single temperature. This happens in alloys like steel. So after pouring, the temperature reduces consistently. At a particular temperature, freezing starts, and then freezing ends over a temperature range, and then the solid gets cooled. So total solidification time is time of pouring to the time at which 100% transformation of liquid metal or molten metal to solid product. So if you see here this phase diagram, it shows at a particular point, for example, 50% copper and nickel alloy. You can see here it's copper nickel alloy. At 50% copper, what happens at a particular point? So this area is completely molten metal, liquid metal. This area is a mixture of liquid and solid, and this is completely solid. So liquid at pouring temperature, you could see here pouring, it is completely liquid. And then after some time, what happens? It starts freezing. At this point, freezing starts. You could see here the temperature decreases, freezing starts. Again, the temperature, then solid, liquid slowly get converted into solid. The amount of solid increases, and at a particular temperature, as shown here, freezing ends, and liquid molten metal completely changes to 100% solid. Then again, it is cooled down to ambient temperature for further application. This is all about solidification of alloys. An important equation we need to study in here is total solidification time. So total solidification time, as I explained, from the time for pouring till the complete amount of liquid metal becomes a solid. So here total solidification time is equal to mold constant times volume divided by area raised to n. V is the volume of casting, A is a surface area. So raised to n, n is a constant which is exponent with a typical value which is equal to 2. Cm is a constant called mole constant. It depends on the material of the mold, it depends on the thermal properties, etc. This is all about an equation which is called Chernus equation. Now, a casting, whenever we design a casting, it is very important to understand a casting with high volume to surface area cools slowly. If you see here, if volume to area ratio is more, then total time required for solidification will be more, keeping Cm and N constant. So if Cm and N are constants, V over area is high, volume over area is high, then total time required for casting will be high. This is already explained in the previous slides. Now shrinkage happens. How shrinkage happens? See, in here, shrinkage of a cylindrical casting during solidification and cooling. If you start, this is completely 100% liquid after pouring, then the starting level of the liquid is like this. After cooling, what happens? The level decreases. Why? Because liquid changes to solid. When liquid changes to solid, contraction takes place. You can see initial solidification along the walls, and then height reduces. Reduction in height, and even along the wall also reduction or contraction takes place because of cooling, or solidification starts at that point. Then you could see here in 2, reduction in height, more reduction in height, and shrinkage cavity, again more amount of liquid metal get converted into solid. And then after some time, what happens? Complete liquid amount will get converted into solid, and there is a chance of production of cavity because of the contraction of the material. Whenever liquid metal get converted into solid, because of the contraction, the shrinkage cavity may get produced. So this is basically an effect of thermal contraction in casting process. So shrinkage allowance, what is the meaning of shrinkage allowance? So whenever we take a casting process, solidification shrinkage occurs in nearly all metals because solid phase has a higher density than a liquid phase. The solidification causes a reduction in volume per weight of the metal, except cast iron with high carbon content. So pattern makers give a solidification shrinkage and thermal contraction allowance by making mold cavity oversized. So what happens is, mold cavity, the shape of the product to be produced, the mold, the exact mold should be oversized. Why it should be oversized is after pouring molten metal, the molten metal shrinks. So that's why we need to account the shrinkage of the molten metal when it get converted into solid. That's why the cavity or the mold must be oversized. Amount by which mold is made larger relative to final casting size is called pattern shrinkage allowance. So how much amount we need to oversize the mold, that is called pattern shrinkage allowance. Now, directional solidification. So to minimize the damaging effects of the shrinkage. So shrinkage is a very big problem in casting because shrinkage cavity is one problem, and the accuracy is another problem because we are oversizing the cavity and we are expecting that the contraction will be this much. So it is desirable for regions of casting most distant from the liquid metal supply to freeze first, and for solidification to progress from these remote regions toward the riser. So the meaning is very simple. During the casting process, if you take a mold like this, so this is the pouring point, we can say this is the pouring point and this is the end, casting end. So whenever you pour molten metal, it should start and then entering the rise, then it should flow and it should reach to the extreme end. So solidification should start from the extreme end and then should progress. So cooling and solidification should start from extreme and then progress towards the pouring cup or towards the riser. This is a good design in a casting process. This is all about directional solidification. So locate the sections of casting with lower volume to area ratios. As I explained before, lower volume to area ratio will get solidified quickly, so it should be away from the riser. So these are some concepts related to directional solidification. So riser design is a very important factor because riser act as a reservoir to supply molten metal continuously to the cavity. Hence, riser design is very important, and we have to keep volume divided by a ratio more than the casting for a riser. So for a riser, V over A, volume to area ratio, must be more than for a casting. Why? If V over A or volume over divided by area as per the equation in here, riser volume divided by area, if it is high, then the total time required will be high. If the total time required is high, then riser solidifies slowly than the casting. If riser solidifies slowly than the casting, then the liquid flow, molten metal, molten metal will get more time to reach to the mold cavity and fill the cavity. That's why riser is made with a higher volume to area ratio in comparison with a casting. These are the references. Thank you. Thank you for watching part 1, week 2 learning material. Thank you very much.